Hello 8th graders, this is the instructional video for Newton's second law, that's ELR 3.5. In this ELR we're doing basically the exact same thing that we did in the lab with the pulleys and the trolleys, except this time we're applying actual numbers with an equation. So to give you a different example, I want you to imagine that you have two wagons and one of them has a really big mass in it, the other a small, and each of these wagons is going to be pulled with the same amount of force. Newton said that the one with the bigger amount of mass in the wagon is of course going to speed up at a smaller rate, so that's why the acceleration arrow is much smaller. In other words, if you pull two objects with different mass but the same force, the larger one is going to speed up slower. They're both going to move, but the one with the bigger mass will do it at a slower rate. So the equation that we're going to use for this is force equals mass times acceleration. And I think of it kind of like the force required to make something speed up or slow down depends on the mass of the object and how fast you want it to go. So that's what the equation looks like. So here's an example of how we're going to use it. Suppose that you have a couple of boxes. The first one has a mass of 1,000 kilograms and it's speeding up at 2 meters per second. And this other box is twice as big. It has a mass of 2,000 and it's speeding up at the exact same rate. So as we just said a second ago, the bigger one is going to be speeding up slower if they're being applied the same force, but this time we're saying, well, they're speeding up the same amount. So which one must be being pushed harder? Of course, it's going to be the bigger one, but we're going to figure out how much force is it going to take to make that happen. So we're going to use our equation, force equals mass times acceleration, and we're just going to plug in what we know. The mass of the first box is 1,000 and it's moving at 2 meters per second, and we multiply that together. It turns out you'd have to push with 2,000 newtons to make this case happen. On the other one, we're going to use the same equation, except this time we're going to use the mass of the second box and still speeding up at 2 meters per second. And that's going to tell us that it's going to take 4,000 newtons. So if you have a box that's twice as massive, but you want it to speed up at the same rate, it's going to take twice the force, is what this is telling us. So here's a different kind of thing to think about. We're also going to, in this class, be talking about, well, what happens if there's more than one force? What if more than one object, or more than one person is pushing on it, or there's a push and a pull? So in order to talk about this, I want you to imagine a box with a mass of 25, and this box is being pushed to the right with 150 newtons. If this were the case, the scenario for figuring out how much acceleration it would have is pretty simple. Let's do that first. That would be force times mass times acceleration, and we would just plug in the numbers that we know, divide by 25. If this situation were happening, a mass of 25 being pushed with 150 newtons, this box would be speeding up at 6 meters per second. But let's make this a little more interesting. What if we were to say that somebody else was pushing in the opposite direction with 100 newtons? Hopefully we can see that this box is still going to be going to the right because that's the greater amount of push. But I want you to answer on your paper, what's going to happen to the acceleration of this box? Is it going to speed up, slow down, or be the same? Please pause the video, think about it, and write your answer right on the paper. If you're still watching, that means that you've paused this video and written down your answer. This box is not going to be accelerating at the same rate anymore. Because there's something pushing against it now, this rate is going to be slower. But we're going to calculate how much slower. So first thing we have to do is figure out the net force, and this is something we've done in the last unit. The net force is going to be how much going to the right minus how much going to the left, and we're left over with 50 newtons to the right. Remember, net forces are vectors, so they have amounts and directions. So we're going to start out with our equation again, except this time we're going to say, in place of the F, in place of the force, we're going to put in our net force, because the net force is like what's left over acting on the box, and that's really all we care about when we're trying to figure out how the box is moving. So in place of force, we're going to put in 50, because that's our net, still a 25 kilogram box. And now we're going to figure out how much it's going to accelerate in this net force situation, and that turns out to be 2 meters per second. So on your paper, we have a rule. If there are multiple forces, you need to find the net force first before you do anything else. If you pick just any old force, you're not going to get the right answer, just like we saw from calculating just the 150 by itself. So here's what I need you to do next. For case number 2, we're going to solve a different kind of a question. In case number 2, this time we're trying to figure out, well, how much is the missing force? We know an acceleration, we know a mass, we have one of the forces, but we're going to solve this missing one right here. So the case is like, suppose you have a box, you're pushing on it to the right, Your friend is pushing on it to the left. You know what's happening to the box. It's moving at 1.2 meters per second in your direction. So what must your friend be pushing with? Well, we can figure that out. But the first thing we have to do is figure out what would the net force, what would it take? What kind of net force would it take? So we're going to say we don't know what the net force is because we have the 1200, but we don't know how much to subtract. So we don't know a net force. So we're going to leave F alone. And we're going to plug in the M and the A, the mass and the acceleration, to figure out what should that net force be. And when we do that, we get 20 times 1.2, straight from the given information, and we get 24 newtons. That means that this arrow and this arrow, when added together, means that our net force should be 24. So now we have to do a kind of a side equation, and we have to say, all right, the total net force has to be our 1200 minus our friend's push of we don't know newtons. We just found out that the net force is 24, so 24 has to equal whatever our push is minus our friend's push. So this is just an algebra problem. When we plug that in, we find out that it's a negative 1,176. And the negative, remember, just means that they're pushing in the opposite direction. Since we said our push was 1200 and we left it positive, and our friend was pushing opposite us, that means they must be pushing with a negative 1176. Now on your paper, it's time for some practice problems. The first one is this rocket problem. You'll need to pause it so that you can read the question. But basically, you're going to be firing a rocket up into the air. You know the acceleration you need. You know how much force the rocket can provide. How much mass can you put on the rocket? Once you've answered this, please check your answer up front before going to the next question. If you're looking at this next question, it means you've checked your answer up front. Now you and your friend are pushing a car after it stalls, and you think your friend is slacking off and not pushing as hard as you. So you know the mass of the car, and you know how much the car is moving, and you know how much you're pushing with. But you need to find out from that information, how much is your friend pushing with, and are they slacking off and pushing less than you? Again, once you have answered this question, please go to the front and check your answer.